Container building and deployment represents a fundamental shift in how we develop, package, and distribute software applications in modern computing environments. A container is a lightweight, portable package that includes an application and all its dependencies, libraries, and configuration files needed to run consistently across different computing environments. Traditional deployment methods often suffer from environment inconsistencies, where applications work on one system but fail on another due to different operating systems, library versions, or configurations. Containers solve this problem by providing consistent, isolated environments that run identically across development, testing, and production systems, eliminating the common issue of "it works on my machine." This module will explore essential tools and methodologies for container building and deployment. We will examine Docker as the foundational containerization platform, cloud-native Buildpacks for automated image creation, and distroless images for enhanced security. The importance of containerization in modern software development cannot be overstated. By 2025, approximately 73% of enterprise applications will rely on containerized infrastructures, representing a fundamental shift in how organizations deploy and manage their software systems. Throughout this module, we will focus on best practices for efficiency and security, equipping you with the knowledge to create portable, scalable, and secure containerized applications that meet the demands of modern software development and deployment. Docker remains the foundational tool for containerization, revolutionizing how applications are packaged, distributed, and deployed across different environments. Docker's architecture consists of 4 key components that work together to provide a complete containerization solution. The Docker daemon runs as a background service, managing containers, images, networks, and volumes on the host system. The Docker CLI provides the command line interface that developers use to interact with the Docker daemon through commands like docker build, docker run, and docker push. Docker Compose enables the definition and management of multi-container applications using YAML configuration files. Docker Hub serves as the central registry for sharing and distributing container images across development teams and organizations. Now let's examine the best practices for creating efficient Docker containers, starting with Docker file optimization techniques. Effective Docker file creation follows specific best practices that significantly impact image size, build time, and security. An inefficient Docker file often uses generic base images, runs multiple separate commands, and copies files before installing dependencies. An optimized Docker file uses specific base images, combines commands to reduce layers, and leverages Docker's layer caching by copying requirements first. Multi-stage builds represent another crucial optimization technique, allowing developers to create smaller production images by separating build and runtime environments. Multi-stage builds utilize multiple from statements in a single Docker file to create separate build and production environments. The build stage includes all necessary development tools, compilers, and dependencies required to build the application, resulting in a larger image size. The production stage copies only the compiled artifacts from the build stage, creating a minimal runtime environment that significantly reduces the final image size. Docker Hub integration completes the containerization workflow by providing centralized image distribution and version management capabilities. Docker Hub provides a complete workflow for image distribution, enabling teams to build, tag, push, and deploy containerized applications efficiently. Docker Hub integration offers significant benefits, including version control, automated builds, team collaboration, and seamless CI/CD pipeline integration, making it essential for modern microservices architectures. Cloud-native Buildpacks represent a significant evolution in container image building, providing a higher-level abstraction that simplifies the containerization process for modern applications. Cloud-native Buildpacks, or CNBs, are tools that automatically transform application source code into optimized container images without requiring developers to write or maintain Docker files. To understand the value of Buildpacks, let's first examine the traditional Docker workflow. Developers must create and maintain Docker files, specify base images, configure dependencies, and handle security updates manually. Cloud-native Buildpacks eliminate this complexity by providing an automated, opinionated approach to container building. The Buildpack analyzes your source code, detects the language and framework, and automatically generates an optimized container image. Cloud-native build packs provide several key benefits that make them attractive for modern development workflows. These include automated image building, comprehensive multi-language support, and production-ready containerization capabilities. Build packs excel at multi-language support, automatically detecting and configuring environments for various programming languages and frameworks, without requiring language-specific Docker knowledge from developers. Perhaps most importantly, build packs generate production-ready containers with security hardening, performance optimizations, and industry best practices built in by default. The efficiency gains from build packs are substantial. Developers using Paquito build packs report achieving 30 to 60% smaller image sizes compared to their traditional Docker file equivalents, while maintaining full functionality. Cloud-native build packs represent a paradigm shift toward automated, efficient, and secure container building. By abstracting away the complexity of Docker file creation and maintenance, they enable developers to focus on application logic while ensuring optimal container images for production deployment. Specialized tools like Co and Jib have revolutionized the way developers build Docker images for Go and Java applications. These tools eliminate the complexity of traditional Docker builds while significantly improving performance and developer productivity. Co is a specialized tool designed specifically for Go applications, while Jib focuses on Java projects. Both tools eliminate the need for traditional Docker files and complex build configurations. Co transforms the Go application build process by eliminating the need for Docker files. It automatically handles dependency management and optimization, resulting in a significantly streamlined workflow compared to traditional Docker builds. Jib integrates directly with Java build tools like Maven and Gradle, enabling developers to build Docker images without writing Docker files. This direct integration results in a remarkable 40% improvement in build speed compared to traditional methods. These specialized tools significantly enhance developer productivity by reducing build complexity, accelerating development cycles, implementing improved security practices, and providing automated optimization. The result is a more efficient and streamlined container development workflow. Co and Jib represent essential tools in the modern container development toolkit, offering language-specific optimizations that traditional Docker builds cannot match. Their adoption continues to grow as development teams prioritize efficiency and productivity in their containerization workflows. Google Cloud Build is a fully managed, continuous integration and continuous deployment service that executes builds on Google Cloud Platform. This powerful service streamlines the process of transforming source code into deployable artifacts. Cloud Build serves as the central hub for your build operations, providing a scalable and secure environment for compiling, testing, and packaging your applications into container images and other artifacts. Cloud Build can import source code from various repositories, including GitHub, GitLab, Bitbucket, and Google Cloud Source repositories. This flexibility allows teams to maintain their existing development workflows while leveraging Cloud Build's capabilities. The service produces various artifacts, including Docker container images, compiled binaries, and deployment packages. These artifacts can be stored in Google Container Registry, Artifact Registry, or other storage solutions for subsequent deployment. The build process in Cloud follows a structured workflow defined by build configuration files. These configurations specify the steps, environment, and resources required for your build operations. The workflow begins with source code retrieval, followed by parsing the build configuration file, such as cloudbuild.yaml. Cloud Build then executes the defined build steps in sequence, finally producing the specified artifacts. Recent updates to Google Cloud Build have introduced several significant enhancements that improve functionality and integration capabilities for modern development workflows. The first major update enables pushing Go modules directly to Artifact Registry, streamlining the distribution of Go packages. Regional build filtering allows developers to optimize build performance by selecting specific geographic regions for execution. Additionally, the ability to specify custom pub subtopics for build notifications provides greater flexibility in integrating Cloud Build with existing monitoring and alerting systems, enabling more sophisticated CI/CD workflows. Google Cloud Build serves as a cornerstone component in modern continuous integration and continuous deployment pipelines, providing the automation and reliability required for enterprise-scale software delivery. In a typical CI/CD pipeline, Cloud Build handles the critical build and test phase, automatically triggered by code commits. It compiles source code, runs automated tests, and packages applications into deployable containers, ensuring consistent and reliable software delivery. By integrating Cloud Build into your development workflow, teams can achieve faster deployment cycles, improved code quality through automated testing, and enhanced collaboration through standardized build processes across different environments and teams. Distroless images represent a revolutionary approach to container security and efficiency. These minimal container images contain only the essential runtime dependencies required for application execution. To understand the advantages of distroless images, we must first examine the fundamental differences between traditional container images and distroless alternatives. Traditional containers include a complete operating system, package managers, shell utilities, and various system tools alongside the application. This creates a large attack surface and unnecessary overhead. Distroless containers eliminate these unnecessary components containing only the essential runtime dependencies and the application itself. This dramatically reduces both size and security vulnerabilities. A compelling case study demonstrates the practical benefits of distroless images. By upgrading Node.js, implementing multi-stage builds, and utilizing distroless base images, developers achieved a remarkable size reduction. The original traditional container image measured 380 megabytes, containing numerous unnecessary system components and dependencies that were not required for application execution. Through optimization techniques and distroless implementation, the same application was reduced to just 60 megabytes, representing an impressive 84% size reduction while maintaining full functionality. The security advantages of distroless images extend far beyond simple size reduction. By eliminating unnecessary system components, we dramatically reduce the potential attack surface. Traditional container images present numerous potential vulnerability points through package managers, shell utilities, and system libraries that are not essential for application operation. Distroless images eliminate these unnecessary components, significantly reducing the number of potential security vulnerabilities and creating a more secure runtime environment. Beyond security improvements, distroless images provide significant performance advantages through reduced resource consumption and faster deployment times. Container startup times are significantly improved with distroless images, reducing from over 8 seconds to approximately 3 seconds due to the elimination of unnecessary initialization processes. Memory consumption is also substantially reduced, with distroless containers requiring approximately 89 megabytes compared to 245 megabytes for traditional implementations, enabling more efficient resource utilization. Distroless images represent a fundamental shift towards secure, efficient containerization. By containing only essential runtime dependencies, they provide enhanced security through reduced attack surfaces, improved performance through optimized resource usage, and simplified maintenance through minimal component complexity. Container portability represents a fundamental shift in how organizations approach cloud infrastructure deployment. This capability enables applications to run consistently across different cloud environments without modification. Container portability allows applications packaged in containers to move seamlessly between different cloud providers. A containerized application can run on Amazon Web Services, Google Cloud Platform, or Microsoft Azure without requiring code changes. This portability is achieved through standardized container runtimes and orchestration platforms like Kubernetes, which provide consistent interfaces across different cloud environments. Hybrid cloud strategies leverage this portability to create distributed architectures that span multiple cloud providers and on-premises infrastructure. Hybrid cloud strategies provide significant competitive advantages by combining on-premises infrastructure with public cloud services. This approach enables organizations to optimize workload placement based on performance, cost, and compliance requirements. One of the most significant advantages of container portability is the ability to avoid vendor lock-in, which can result in substantial cost savings and increased negotiating power with cloud providers. Traditional vendor lock-in scenarios trap organizations with high migration costs and limited options. Container portability eliminates these constraints by enabling seamless movement between providers with minimal overhead. Windows Server Annual Channel for Containers represents a significant advancement in container portability, streamlining the upgrade process for both Windows and Linux containers. This annual channel approach provides organizations with predictable update cycles and improved compatibility between Windows and Linux container environments, further enhancing overall portability. Container portability and hybrid cloud strategies together create a powerful foundation for modern enterprise architecture. Organizations can achieve cost-effectiveness, flexibility, and competitive advantage while maintaining the freedom to optimize their infrastructure choices. Container optimization for Cloud Run requires specific strategies to maximize performance, security, and cost efficiency. We will explore key optimization techniques and examine emerging trends shaping the future of containerization. Cloud Run optimization begins with using distro-less base images, which significantly reduce both security vulnerabilities and image size by eliminating unnecessary operating system components. Implementing automated CI/CD pipelines through Cloud Build ensures consistent, reliable deployments while reducing manual intervention and potential errors in the deployment process. Minimizing application dependencies directly impacts startup performance, reducing cold start latency and improving overall responsiveness of containerized applications. Proper concurrency tuning, combined with memory optimization, ensures efficient resource utilization and cost-effective scaling in serverless environments. These optimization techniques deliver measurable performance improvements. Container startup times can be reduced from 2.5 seconds to under 1 second, while image sizes decrease dramatically from 380 megabytes to just 60 megabytes. The containerization landscape is rapidly evolving, with several key trends shaping its future. Kubernetes maintains its dominance, accounting for 83% of container orchestration deployments worldwide. Podman is experiencing significant growth due to its daemonless architecture, which enhances security by running containers as non-root users and eliminates single points of failure. WebAssembly integration represents a paradigm shift, enabling containers to run efficiently at the edge with near-native performance and enhanced portability across different architectures. Container security has become paramount, with organizations implementing comprehensive tools and practices to protect applications throughout their entire lifecycle, from development to production. Artificial intelligence and machine learning are being integrated into container orchestration platforms to optimize resource allocation, predict scaling needs, and enhance anomaly detection capabilities. Container optimization and emerging trends indicate a future focused on security, performance, and intelligent automation. Organizations adopting these practices will achieve significant competitive advantages in cloud-native environments.